This video is on the single index model. So a single index model is basically the empirical analog of the CAPM theory. So it assumes that returns of asset I and asset J co-move because both assets have exposure to the same underlying risk factor, which here would be the market return. So using equations, we could write that idea as follows. So here we basically display a single index model for asset I and J with the market portfolio M being the common risk factor. Beta I is the amount of asset I's systematic risk. Alpha I is the part of the expected risk premium of asset I that the single index model cannot explain. And epsilon I is the firm-specific return shock of asset I. Now the same holds for asset J. So notice that the single index model assumes that different firm-specific return innovations, here epsilon I and epsilon J, are uncorrelated with each other and with the single index. And in addition, these disturbances are zero on average. That single index model implies the same expected return beta relationship as the security market line in the CAPM. Equation-wise, it means the following. So notice, according to the CAPM, the non-market risk premium alpha I needs to be 0. Yet in real-life applications, it can be different from 0 and hence needs to be explicitly accounted for when estimating a single index model with data. Now let's have a closer look at why different assets co-move in a single index model. We do that through some simple equation-based manipulations. So let's work out what the covariance of excess return I with excess return J looks like. It's the covariance of, now you plug in the single index model for asset I and for asset J. That gives you the first equality sign. And now you ask yourself which terms are co-moving with each other. Alpha is a constant, doesn't co-move. Epsilon I, epsilon J is orthogonal to each other and orthogonal to the market. So the only terms that co-move here are beta I Rm minus Rf and beta J Rm minus Rf. So that covariance boils down to beta I times beta J times the variance of the market. Now that says that two assets co-move in a single index model because both have a beta exposure to the common risk factor Rm. Now we can also look directly at the pairwise correlations that a single index model induces. So let's work out what the correlation looks like between the excess return of asset I and the excess return of asset J. Now the correlation is defined as the covariance divided by both standard deviations. Now work out yourself that coincides with the product of both betas times sigma square m divided by sigma I times sigma j. Now basically there is not much to work out as we've just shown that in the previous calculation step. Now what we now do is we multiply the numerator and the denominator by sigma square m. That gives us that the correlation between both assets consists of these two products. And you can rewrite that as the product of both correlations. Now that last equation states that the correlation of two assets within that single index model coincides with the product of the respective correlation coefficient with the single factor. Now, the single index model has also a very practical advantage for portfolio optimization. Using a single index model reduces the required number of estimates for the expected returns and for the covariance matrix in a Markowitz portfolio selection process. Now let's consider a portfolio with n equal to 50 assets. Assuming that their returns follow a single index model means one would have to estimate 50 estimates for alpha I, 50 estimates for the betas, 50 estimates for sigma square epsilon I, the idiosyncratic risks, and one estimate for the expected market risk premium, and one estimate for sigma square m. Now in total, we would have to estimate 152 input parameters. Now these are still quite a lot, but it's roughly a 90% reduction relative to the 1,325 parameter estimates that a full mean variance portfolio optimization input list requires. But as expected, a dimensionality reduction of that size comes potentially at a cost. The mean variance portfolio with mu hat and sigma hat being estimated by a single index model can be substantially inferior to a full covariance and expected return estimate using sample data. Now the solution will indeed be inferior if the firm-specific returns of different assets co-move with each other. That is because the single index model builds the covariance estimate sigma hat with the assumption that epsilon I and epsilon j have a zero correlation. Hence, it's important to ensure that the single factor model that you use implies that, statistically speaking, firm-specific return shocks are uncorrelated with each other. So let's take a step back and ask the following question. How would a portfolio manager combine the single index model with the portfolio selection approach of Markowitz? Well, basically that manager would use 4 steps. Step number 1, he would do a market-wide analysis to estimate the expected market risk premium, mu m minus rf, and the expected amount of market risk, sigma square m. Now, in the second step, he would do a statistical analysis to estimate for all assets their respective beta and sigma square epsilon. Step number 3, the asset manager might use security analysis, machine learning, or any other secret wizard trick to identify the alpha coefficient of every asset. And step 4, given what we've said above, he would assume that the assets holding period returns follows a single index model with the respective mu and sigma estimates, and then he would plug that into the Markowitz portfolio optimizer. A typical choice for the index would be the S&P 500 for an investment in US equity, and the Euro Stock 600 for an investment in European equity. Now, a final word from my side. Using the full covariance matrix sigma as in the mean variance portfolio selection approach of Markowitz will be superior to the single index model approximation if all entries of sigma can be estimated with high precision. But in practice, it's difficult to estimate pairwise correlations in an accurate way. It's therefore to be expected that a low-dimensional factor model will be less prone to the garbage in, garbage out problem. But in order to be really sure, one needs to do careful backtesting and accurate assessment of the adequacy of the factor model at hand.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.